Thanks. Okay, so today we're going to talk a little bit about intermolecular forces. So intermolecular forces and their impact on physical properties. Okay? So what we want to do then is to sort of get a quick inventory of what are the intermolecular forces, what is their origin, what are their relative strengths, and then we would get inventory of the physical properties, which are the ones that are common and we look at on a fairly regular basis. And then we sort of tie the two inventories together and look at how the physical properties of a substance are dependent upon the intermolecular forces. And as it turns out, the physical properties depend largely on the intermolecular forces, but there are other factors that contribute to them, particularly the mass of the molecule and the shape of the molecule. And we'll tease out those nuances as the lecture progresses. We will probably spend 2 lectures on this topic. Let's go ahead and start then on the first issue. So what are the intermolecular forces? And we will sort of do a dance between intermolecular forces and physical properties as we go along, as we build our repository of information. So what are the intermolecular forces? And really quite simply, those are the forces, the bonds of attraction in this case, that exist between molecules. Okay? So these are very different now from intermolecular forces. Now let's say, for example, I'm dealing with molecules of methane. So if I look at molecules of methane, so one methane molecule and another methane molecule, right? So within this molecule of methane, and within this molecule of methane, there are very short, very strong carbon-hydrogen bonds. Right? These are quite strong bonds. Again, because H is the smallest element in bonds, carbon is a second period element and is in the middle of the period. And we talked about why organic chemistry, why carbon gets its own sub-branch. And one of the reasons was because carbon was small, and that meant it would make short, strong bonds. Strong bonds meant stable compounds, right? Because they would not decompose under ambient conditions. So the bonds that are within the molecule, these are intramolecular bonds, right? Intramolecular, right? These are bonds that are within the molecule. So intra means within. So intramolecular bonds are the bonds that make up the molecule. And for many organic compounds, certainly for the hydrocarbons, those bonds are very strong, right? They're carbon-carbon bonds, and the carbon-hydrogen bonds. Those are very strong bonds. But that's not what we're discussing here. We are discussing the bonds between one molecule of methane and another molecule of methane. We are talking about these bonds, and these are intermolecular bonds, so intermolecular forces. So those are bonds between molecules. Now, I can say something really simple here at this point. Methane is a gas at room temperature. So what does that really mean? Well, that means that 25 degrees Celsius, and really, methane is a gas, even at 0 degrees Celsius, even at minus 50 degrees Celsius, methane is a gas. So let's start with minus 50. So methane is a gas at minus 50. Which is very low. So what that means is that minus 50 degrees Celsius provides enough thermal energy not just to melt solid methane, but to boil liquid methane. Right? So at minus 50 degrees, we can overcome all of the bonds between the individual methane molecules. Now, whether it's solid methane, liquid methane, or methane gas, they're all containing CH4. We are not perturbing, we're not breaking the bonds within methane. Right? So whether water is ice, liquid water, or steam, they're still water molecules. Right? We're not doing chemistry when we change phase. Those are physical properties. Okay? So within methane, whether we're solid, liquid, or gas, we still have a carbon bonded to 4 hydrogens. And it's all going to be tetrahedral. But what is happening is we are overcoming the bonds between one methane molecule and another. So at minus 50 degrees, we provide enough thermal energy to completely break the bonds between one methane molecule and the other. That's what we define as a gas phase. There are no residual bonds between the molecules in a gas phase. Okay? So minus 50 degrees is able to overcome all of those intermolecular forces in methane, which must mean those forces are awfully weak in methane. From minus 50 degrees to provide enough of a thermal punch to break them all, those bonds must be weak. But that has nothing to do with the fact that these bonds are very strong. Right? The intramolecular forces are not the ones we're disturbing when we do phase changes. We are disturbing, and in some cases completely breaking, the intermolecular forces. Okay? So let's not mix the two things up. So when we talk about a substance having a very low boiling point, that's got nothing to do with the bonds within the molecule. That has everything to do with the bonds between the molecules. So let's have a very clear picture in our minds which kind of bonds we're referring to. We are not referring to the covalent bonds, the intramolecular bonds that make up the molecules. Not our concern. That is the concern of chemistry, of chemical reactions. We are concerned here now with physical changes. And what is the impact of the intermolecular forces on physical properties? Okay, so let's talk a little bit then about, and this really is going to be the essence of the conversation as we look at the different types of bonds and then on their impact on physical properties. Alright, so we're going to start this in a very weird place by looking at bonds that are not really intermolecular. We're going to look at ionic bonds. So let's get a sense of ionic bonds, and you remember this from your Gen Chem and from high school if you took high school chemistry. So let's imagine I have a sample of sodium chloride or something. So sodium chloride consists of Na plus, Cl minus, and every Cl minus is surrounded on all sides by an Na plus, and every Na plus is surrounded on all sides by a Cl minus. Right, so what we have in ionic compounds is what's referred to as a lattice. Right, we have a regular arrangement in which every ion is surrounded by what's called its counter ion or its Gegen ion. So the counter ion is the ion of opposite charge. Gegen means opposite. We talked about when we said things can be E or Z in terms of stereochemistry about a carbon-carbon double bond. We said the E came from the German word on Gegen, which means essentially opposite or opposite. So Gegen means opposite, so it's a counter. So the sodium cation is the Gegen ion or counter ion of chloride. Chloride, the chloride anion, is the Gegen ion or counter ion of sodium plus. Okay? Okay, so what can we say about, now again, this is not intermolecular because these ionic compounds don't form molecules. So the term intermolecular doesn't really apply. But it's a good place to start the discussion because you can see the impact immediately. So let's describe the bonding in sodium chloride. So every cation is surrounded top, bottom, right, left, front of the board, and behind the board by a chloride. Every chloride is surrounded top, bottom, right, left, front of the board, and behind the board by a sodium plus. Okay? If I look at if you remember this equation, where we look at the force of attraction depends upon the sizes of the charged particles. So it depends upon the charge, so Q is a symbol for charge, and some people use uppercase Q, right? It doesn't really matter. But the force of attraction between oppositely charged particles depends upon the sizes of the charges, right? It depends linearly upon the size of the charges. I'm just going to write it in here, but you remember this as well. It depends inversely upon the square of the distance between the particles. I'm going to focus on this relationship, right? So the force of attraction depends upon the size of the charges. Now you might say, well, the charge in chloride is only 1 minus. The charge in sodium is only 1 plus. And 1 is a small number. After all, 1 is a number just above 0. That's not true at all. Right? There are an infinite number of numbers between 0 and 1. Okay? And we've seen cases where I'm dealing with, for example, HCl, where there is a delta minus charge on the Cl and a delta plus charge on the H. That number is less than 1. Right? And this delta is fairly large because chlorine is very electronegative. But if I were dealing with, say, HBr or HS, this is even a smaller delta value. Okay? So on the grand scheme of things, particularly when it comes to charges, 1 is a big number. Right? It's much bigger than 0.01 or 0.05 or whatever. Okay? So 1 is a big number. And what that tells me then is that the force of attraction between these charged particles in an ionic compound, say sodium chloride, that force of attraction is very strong. And in any event, I am picking 1 as the unit charge, because in reality the charge in those things is really a certain number of coulombs, right? And that's 1.6 by 10 to some number of coulombs. So if you look at it from that perspective, it's actually a big number. I have just normalized that as 1. So the bottom line is the force of attraction between a chloride, an individual chloride, and an individual sodium, that force of attraction is big. In other words, it's a strong bond. But it's not just 1 of them. For sodium chloride, there's 6 for every ion. For the chloride, 1, 2, 3, 4, 1 in front of the board, 1 behind the board. So every ion in sodium chloride is held in place by 6 very strong bonds. They're held in place by 6 very strong bonds. Okay. So what are the consequences of having 6 very strong bonds holding my lattice together? Let's see. What are some of the things we expect to see? How will that play out? Now that we understand, well, it's not intermolecular, but the interparticle forces in sodium chloride. How, for example, would that play out in some of the physical properties? And what are some of the physical properties we're going to look at? We're going to look at what we call collectively the phase transition temperatures. So what are those? Those are the temperatures at which the sample transitions from one phase to the next. What does that mean? We're looking at the melting point, right? The melting point and the boiling point, right? the MP and the BP. Now, there are also the sublimation temperatures, which we're not going to really consider for much of the discussion. So one of the things we're going to look at is melting point and boiling point. We're also going to look at the phase at room temperature. In other words, is it solid, is it liquid, or is it a gas? And really that's related to the issue number one. If it is solid, we're going to ask, is it crystalline, or is it powdery, is it amorphous? Right? Is it crystalline or is it amorphous? And there are a lot more that we can go into, but for now I just want to give us an introduction. So now that we understand the interparticle forces in sodium chloride, what would I expect to happen for sodium chloride's melting point? So I have to ask myself the question, okay, fine. What does melting point mean? What happens when something melts? Well, I'm going to draw a cartoon. I'm going to say, here is my solid. And these are the interparticle, and those could be intermolecular, or in this case, interionic. Those are my interparticle bonds, the little dashes. In the solid, the particles are capable of moving up and down. I can move up and down, left and right, forward and back, or some combination of those. I can move at an angle, right? But the motions you're allowed are up and down, left and right, forward and back. In other words, I can vibrate. Molecules in a solid can't rotate. Molecules in a solid can't translate. In other words, I can't go from here to here and go away. I can go here, but if I do that, there is a force pulling me back. So I can oscillate about that center. That's vibration. So in the solid, all I can do is vibrate. I can't rotate, and I can't translate. I can't go from point A to point B without coming back. Let's imagine I take the solid, and I heat it. So there's my solid, and I heat it. And you remember from your basic physical science, what that's going to do is melt it. So I'm going to end up with my X's, and there will still be some bonds between them, but now my particles are capable of motion, of more motion. So now I can swim about, I can certainly vibrate, right? I can certainly vibrate, but now I can rotate, and this particle can move from here to the other end of the tube, or whatever. This is my liquid phase. So the particles now have more freedom. There's more motion that's available because I've overcome the bonds that are locking me in the solid. Right? So when I go from solid to liquid, I am overcoming the bonds that are locking me in the rigid lattice. That's what happens when I melt. Now, what happens if I continue the thermal assault on my sample? What happens if I keep heating it? Well, eventually what's going to happen is I'm going to completely break any of the bonds between the X's. And I'm going to end up with a gaseous phase, where there are no more bonds between X and X. Okay? So the particles are able now to move, but whereas these were what we call condensed phases, so if I had a test tube with my solid, right, with a block of my solid, right, that's a solid, and I heat it, I'm going to end up with my test tube containing the liquid. And if I heat that, I end up with a test tube containing nothing, because all of the substance has gone away. Okay? So if you notice, a big part of what happens when we heat is we increase the mobility of the particles. We're overcoming bonds, and in the process, we're increasing the mobility of the particles. The bonds are what keep us together. The bonds are what keep us in a condensed phase, whether it's solid or liquid. So with that little cartoon in mind, what do I expect the melting point of an ionic compound to be? Sodium chloride, for example. Well, look, the bonds between these are many and strong. So if I'm going to try to break a strong bond, I've got to put in a lot of energy. And if I'm not just breaking one, but I'm breaking 6, the energy cost is going to be massive. Right? Well, the melting point is a measure of how much thermal energy I need to go from the solid to the liquid. The melting point is a measure, the melting point is not the energy. Right? Melting point has units of degrees Celsius or Fahrenheit or whatever. That's a temperature. Energy has units of joules. Melting point is not energy. But it is a proxy for the energy. It is a measure of the energy. The more energy I need to put in to melt the substance, the higher the melting point. Okay? So, because I need to put in large amounts of energy to break 6 very strong bonds, the melting point is going to be high. So I'd expect ionic compounds to have high melting points. Well, that means that at room temperature, 25 degrees Celsius, we don't have anywhere near enough energy to break those bonds. So I expect those ionic compounds to be solid at room temperature. But when they're solid, do I expect them to be crystalline or powdery? Well, let's think about it for a second. If I have a room, if I'm a kindergarten teacher, and I have a group of students sitting in class, and I rule my class with an iron fist, so nobody moves on penalty of death, well, there's going to be a massive amount of order in the classroom. So if I impose a rigid rule, if the force I impose on people is strong, people will stay put in their positions. But if I don't have control, if my force that I exert on people is weak, then the kids are going to run all over the room. So because the bonds in ionic compounds are very strong, and because they are very many, and because they are multi-directional, right? They are multi-directional, right? In other words, they exist in 3 dimensions, right? Y, X, and Z. I'm going to have great order on the particular level, which will expand in scope. So you can imagine a small block like this with them in front and behind, expanding, expanding, expanding. So order on this scale becomes order on the grand scale. So if everything is ordered, it's going to look crystalline. That's what crystalline means. It's crystalline if the particles are locked in particular positions. Well, I expect that for ionic compounds. Why? Because the bonds are strong, so they're going to hold the particles in place. The bonds are many and multidirectional. So I've got a 3-dimensional order imposed upon the lattice. That is going to manifest itself on the bulk scale as crystallinity. So the strength and the nature of the bonds in ionic compounds explain for me why ionic compounds are solid, are crystalline solids at room temperature, while the melting points are high. Right? Their boiling points are also going to be high. And why is that? Well, to begin with, their melting points are high. So you've already got to put in a ton of heat to melt them. But to boil, I must now break the residual bonds. And the energy needed to separate something positive from something negative is going to be high. You're going to have to pay for that. Because the natural tendency is for them to collapse. So to break these residual bonds in the ionic compound, I have to pay an additional amount of energy. So ionic compounds are going to be crystalline solids at room temperature. They're going to have high melting points and high boiling points. I can infer that based upon my understanding of the nature of the bonds in ionic compounds. That is the game we're going to play. We are going to identify the origin of the bonds, as in this case, I have a cation and an anion, right, formed by electron exchange. I'm going to describe the strength of the bonds, the distribution of the bonds, and then see how those impact the physical properties. Okay? Okay, so let's go ahead and start by looking at, so we're going to ignore now ionic, because that was a good example. And I tell you what, we are going to, since I have melting point and boiling point on the board here, let me also, before I go to the other intermolecular forces, let me sort of amplify these a bit. So I'll take care of this all at once. So for the melting bit, I think we've described that fairly well. What we're doing when we're melting a substance is we are breaking the interparticle bonds. We're overcoming the bonds that are locking us in a solid. We're not overcoming all the bonds because there are still some bonds in the liquid. That's why they're trapped in the glass. If there were no bonds between them, there are no force of attraction, they would go out of the container. In other words, we would boil and just have a gas. So in the liquid and solid, in my condensed phases, there are forces of attraction locking them in the condensed phase. Right? The bonds are stronger in the solid than in the liquid, which is why I have the heat to overcome them to some extent. But let's also describe the phase changes in another way. Ultimately, what I'm doing is I'm mobilizing the particles. I'm increasing their mobility from vibration to rotation and translation. So what do I need to overcome for that to happen? Well, absolutely, I have to overcome the intermolecular forces, the interparticle forces. So the stronger those forces are, the more thermal energy I need, the higher the melting point. I have to, the more of them I have, the more bonds I have, then the more energy I have to pay, the higher is the melting point. So we're looking at the nature of the bond, strong, weak. I'm looking at the number of the bonds. But I also have to look at the mass. Because if fundamentally I'm trying to mobilize a particle, it's harder to move something heavy than to move something light. So if I have particles that are big and heavy, I'm going to have to put in more energy to move them than if the particles were small and light. So I would expect then the melting point to depend upon the nature of the bond vis-a-vis the strength of the bond. It would depend upon the number of those bonds. The more bonds I have to break, the more energy I put in. But I'd also expect it to depend upon the mass of the particle. All things being equal, the heavier the particle, the more thermal oomph I must put in to get it to move. Because fundamentally, changing phase is about changing motion. So what are my factors? I'm looking at the bond, in other words, its nature, and nature deals with the strength and the number. And I'm also looking at the mass of the particle. Okay? What about boiling? What do I have to do to boil a sample? Well, in my liquid, when I boil it, what am I doing? Well, I'm lifting molecule by molecule out of the liquid state. Okay, that's the description of boiling. Great. What do I need to overcome? Why do I need to put in energy to boil it? Well, I need to put in energy because there are bonds between the particles in the liquid. Right? These bonds. Because we didn't overcome them all when we melted from the solid to the liquid. That's why it's still a condensed phase. So I must break those bonds. Alright. The stronger those bonds are, the more thermal energy I need to put in to break them. 1. The more bonds I have, the the more thermal energy I need to put in to break them. But I am also lifting the molecule against the pull of gravity. Right? That's what we're doing, right? We're lifting the molecule out of the liquid state into the vapor state. So obviously, if the molecule is heavy, right, it's going to take more energy to lift it, right? And therefore, the boiling point, which is a measure of the amount of thermal energy I need to boil, that value is also going to go up. So I expect the boiling point, the factors that affect the boiling point, to mirror the factors that affect the melting point. Stronger the bond, the more energy I need to put in, higher the boiling point. The more bonds, the more energy I need to put in to break them, higher the boiling point. The heavier the molecule, the more massive the molecule, the more thermal energy I put in to lift it, right, against the force of gravity. Okay. All right, good. So let's go ahead and start doing an inventory of the intermolecular forces. And I'll start with an example that I had written on the board earlier, which is, let's say, HBr or something. So if I look at a simple molecule like HBr, there is a dipole moment about the molecule that arises from the difference in electronegativity between H and Br, creating a positive dipole on the H and a negative dipole on the Br. So when I have a sample of HBr, I'm dealing with billions of molecules of HBr. Well, they will spontaneously arrange themselves so that the delta plus of one HBr is interacting with the delta minus of another. Okay? And this interaction is called a dipole-dipole bond. This interaction between the dipoles of one HBr molecule and the dipole of another, that's called a dipole-dipole bond. The names for these are very unimaginative. This is the negative dipole on the Br, that's a positive dipole on the H. The bond between them is a dipole-dipole bond. End of story. No imagination whatsoever. So the one type of intermolecular force, one type, is dipole-dipole. That's a dipole-dipole bond. Right? And the bond is nothing more than a force of attraction. Now, forces could be attractive, in which case they're a bond.